after like seeing you 2-3 times, and then I'll get it.
1, 2. Just checking if this is working. Jonathan Ortiz. Hello. Hello. Okay, I put this on airplane mode. Who's that? Ivan, how you doing? Good to see you. Good to see you. Good to see you. Trying to get this rotate device back.
How did you guys do?
We did pretty good.
Yeah.
You felt really comfortable yesterday, huh?
Yeah.
I mean, they just had us take everything off the board and just
Do that.
Sorry, guys. Trying to figure this out right here.
Wasn't troubleshoot.
not yet. So you guys feel comfortable, huh? You guys chose me. On the furnace, what kind of calls did he give you?
Don't understand why it says.
The first one was my transformer, and then second.
Oh, wasn't getting voltage?
Yeah.
All right, guys. Just give me 1 second. Brian. Hey, Brian. We're going at we should be there at 10. Hey, how's it going? Good to see you. Good to see you. Come on in. Come on in. You're good. You're good. We'll start right now, guys, in a couple minutes. 4 minutes. I'm not just gonna record today's session, but we're gonna go over permanent split capacitor motors. So we're gonna take notes. Yeah. Love from California City. Hey, what's up? No worries. No worries. I can. I'm gonna write everything on a. I mean, it would be good to, because the idea is if you get that on the unit, I'll give you paper.
Yeah, give me paper so we write it.
Yeah.
We're not doing writing.
Yeah. No, you're good. You're good. Yeah, I don't have any lectures in Udemy. That would be nice. Texas. Hey, I'm trying to still understand this, guys here, but we're gonna go live right now. I'm gonna go over permanent split capacitor motors in a couple minutes. Hugo from Washington State, man. Greetings. But yeah, it would be nice to have classes and lectures in Udemy. It's not a bad idea. Thank you for bringing that up. Austin, Chicago, man, the whole country. This is awesome. Yeah, we're gonna have a 30-minute lecture on permanent split capacitor motors. So it's gonna be nice. New York, that's awesome. New York in the house. I was just there. Yeah, a couple weeks ago. I think it's gonna start getting cold now, but um, I don't play. I don't play Clash Royale, but I do play FIFA a lot. So, sorry. Going back to the convention, I'll be there. So they have a class from 10:30, from 10:30 to 11:30. So it starts at 11 to. It's from 11 to 7 o'clock. The actual expo, but they have a class from 10:30 to 11:30 for those starting off out in the field. So if you're planning on going to iHacky in Pasadena, the HVAC expo on this Thursday, they do have that class for those starting off from 10:30 to 11, but it's from 11 to 7. That's when the class when the class is. New Orleans, Louisiana. Hey, man, we got everyone today. Let me see if I can start the class now. I keep getting this connection is locked, rotate device. I'm gonna have to figure that out at some point. But okay, well that's fine. For today, we'll just go ahead and do it like that. Okay, I'm just gonna do that for now. All right, let's go ahead and get set up.
I did boxing. Like one of my first jobs I did, it was I used to be making boxes inside the printing shop.
All right, Let's go ahead and get started.
4 months, bro.
6 o'clock.
Now just put on my headphones, bro. I just go, you know, you have to find the floor, bro.
Yeah.
And after that, they took me to
Right.
cutting and cutting up, cutter, yeah,
Alright.
but it was all.
Let's put this right here. Right.
have to
You should be
work.
able to see me from here.
It's all computer on the computer, and you have to put it right, like which side. It comes out, imagine, so
So,
business cards, it comes out like this.
how was your day today, Andrew? All right.
So you
Yeah.
have to,
Yeah.
you have to cut
Nice,
all of it.
nice.
And then you have to turn it.
On Tuesdays, I didn't work yesterday night, so I'm making it up tonight. But I'm basically here all day. But it's all right. 2 days out of the week, my life is here in the lab, so it's all good. It's all good. So, all right. So we'll go ahead and get started, guys. Welcome. I know we're still waiting on two other students. I got a message, yeah, so they'll be here in a bit. But we'll go ahead and get started. They can get the notes later. I hear you're doing good with schematics, so you two are on it. Good job. As you know, I have the big ladder and pictorial schematics, so we can start using those on the actual package unit and start seeing where those wires relate to on the actual unit. That's the whole idea. And don't get me wrong, the panels that we're doing, the contactors, light bulbs, it's cool.
This is harder.
But yeah, sure, you want to see that's harder. And the idea is that is for you to be comfortable with the unit, right? And to be honest, all the package units, all the air conditioning systems, when you buy a system, the high voltage is already all wired in. And we're not talking about the power you're bringing in from the panel. We're talking about the wiring that's already built in the system. It's already all wired. You're just installing the thermostat and the low voltage wiring as you've done already, the duct work. Troubleshooting, though, is another thing. Is that a contactor? Is that a bad compressor? Do I have power coming in? Did my breaker trip? My thermostat, is it on? Do I have a bad transformer? But today, I know yesterday you guys were talking about control boards. Today we're going to go over PSC, permanent split capacitor motors. So there's going to be a couple of notes with this. PSC, another word for that is permanent. And I am just going to explain it. I'm going to just explain it as simple as I can get. If you want to get deep with this subject, there's a lot of videos online, a lot of articles. I'm just going to explain it how it is, okay? So permanent split capacitor motors. These are basically motors that need a capacitor, okay? And we're going to talk about two motors today. We're going to talk about the compressor and the indoor motor, a PSC, a permanent split capacitor motor. So when you see all these wires, people get a little intimidated, but it's actually not too bad. So compressors, and I'm referring to single phase, right? This is single phase power. But when talking about a compressor, okay, let's go ahead and put this, let's see, how am I gonna do it? Let's do like that. Okay, and then go like that. Start. All right, and then my comment, all right? So go ahead and start drawing that. So you guys should kind of have an idea what that is or what's that symbol stand for. What do you guys think that is, that symbol?
It's not calling for, it's closed.
It's closed, but is it a pressure switch, a temperature switch?
It's a switch.
A temperature switch, right? That's a symbol for temperature, but it is a normally closed switch, a normally closed switch, okay? We'll talk about that right now. But a single phase, in regards to a compressor, right? This is a compressor. It has two windings, right? You got the start winding and you got a run winding, okay? Start and run winding. If you were to look at both, and these are just coils, right? You guys are used to coils already. Your contactor coil, right? Right, you guys are used, it's the same concept, okay?
When you say single phase, is that meaning a single phase of on the thermostat? Or
good.
You have one thermostat, or what is it?
Yeah, good question. So, single phase power. So, let's say, do you guys have a split system at your house? An air conditioning system at your house?
I used to have it.
Yeah?
Yeah.
Well, let's, the packaging that we're going to be working on today, right? Today,
Yeah.
you have two lines of power coming in, line 1, line 2, and ground. That's single phase, because you only have two lines of power. Now, I don't know why they don't call it double phase, but it's either single phase or three phase. See, single phase comes in with 2 hot legs.
Uh-huh.
Three phase comes with 3 hot legs. That's it.
That's it.
That's it, yeah.
Okay.
So, 3-phase power, your compressor, because it's 3-phase, it doesn't need a capacitor. But we're not going to go too deep into 3-phase. We're just going to go over single phase. So the idea is that we have 2 coils, just like this, right? You guys have seen these coils, right? Mm-hmm. Inside the compressor, you have 2 coils. Which of these coils do you think has more resistance? Which one looks like it has more resistance by looking at this right here? The start. You see, it has more resistance. The run winding has less. Okay, and we're going to talk about this as we go down to the lab, but the way you check these, and I'll explain the science behind this, but you're going to check resistance, okay? And you're basically going to have 3 pins coming out of that compressor. And it's going to literally look like this. 3 pins on the back of that compressor. And so on that compressor, if you were to open it up, that's how it would look like inside. So let's do this. From run to common, from start to common, and from run to start. And we're talking about resistance, okay? All right. So let's say we get, right? And like I said, I want to show you guys down there, but let's say between a run to common, I get 0.8 ohms, right? Between run to start, I get 1.2. And these are just numbers, right? They are similar to what you guys are going to be seeing. And right here, 1.2 and 2.0. Okay, there we go. So from here to here, I have 0.8 of resistance. From here to here, I have 1.2 of resistance. And guess what? When I check from here to here, I'm going to have 2.0.
It's the total.
That's the total. It's going to be the total. So when you check run to start, it's going to be 2.0 because you're adding the 1.2, which is your start winding, and then your 0.8, which is your run winding. When you add both of them, 2.0.
Is there a case that's not the same?
So in my experience, I was going to get to that. Good question. I was going to get to that. It might be 0.9, and that should be 2.1. It's not the end of the world. Okay, now, if you get like, let's say you add everything, it should be 2.0, but this one's kind of off. Let's say it's like 0.5, and it should give you a 2.0, and you're like, okay, something's going on with the run winding. But guess what? If it still turns on though, just let it be. Let it be. But you as the technician, you can tell the customer, hey, something's going on with the run winding. They're not gonna understand all the lingo, but something's going on. It could go bad, but that number should be equal or closer to 0.8 to give you the 2.0 when you check it.
So will that be the coil?
Something in the run winding is going on. It's probably going bad, but it's not so bad where it's gonna stop working. I've gone to some where it's like the numbers are not the same, and it's off by 0.1, not the end of the world. If it's off by 0.5, but it still turns on, just let it be. Yeah, just warning, it's coming, okay? Okay, so Now, if you go to a job and guess what? 0.8, let's say you get this, open line. Something happened to the winding, bad compressor, you gotta replace it. And over here too, let's say between start to common, this one you get 0.8, and between start to common you get open line. Something happened to the start winding, okay? Something happened to it. All right, but let's say it's working.
You have to replace the whole compressor.
Yeah, you gotta, every time we replace a compressor, you have to change out the compressor, the filter dryer, and of course always brace with flowing nitrogen, always, to get rid of that sud. But yeah, you gotta replace the compressor. It's a big job. You gotta recover, you gotta unsweat, you gotta flow nitrogen as you brace, replace the filter dryer, pull a vacuum, and then charge the system up again. It's a big job. So this is one way, okay? We just check, right? You gotta ohm it out. You're also trying to avoid it saying open line. And obviously if it says open line, right? Let's say it's not turning on. Okay, let me turn off power, and you go to it and it's open line. Okay, that's the problem. There's something going on with that winding. But going back to the temperature switch here, this is very important, okay? This temperature switch. What do you think? And I would expect maybe Ivan and Andrew, yeah, you guys to kind of know a little bit more because you guys took the class. What can cause the compressor to, remember, this is a normally closed temperature switch, but it's on the top, right? The little circles here. So if temperature rises, the switch opens. What can cause that compressor to overheat? To get too hot? What happened?
Not enough refrigerant running.
There we go. Good job. A high superheat. Good job, Andrew. A high superheat, you're low on charge. You need that vapor temperature to be as cold as possible. A good superheat to cool down the windings. Guess what though? You're low on charge. This is what's going to happen. It's going to open. Boom. Okay? So you go to a job, right? You go to Mrs. Applebottom's house. You go to the system. Power's off, right? Always turn off power. You're going to check the compressor because it's not turning on. You get your hand and just touch it, and it burns you. It's hot to touch. It literally, when a compressor is under charge, you're going to feel it in your hand. It's super hot. You can't put your hand there. But let's just say you go to the job, disconnect power, pull the plug, check your pins, and you check between this one and here. And let's say you get this. Between run to common, you get open line, and run to start, you get open line. Is it a bad compressor? Think about that. You get open line on your run winding and your start winding. You get open line. Is it a bad compressor? Why?
Because it's open.
There we go. Good job. Good job. Because it's open. But people are going to be like, it's bad. It's not bad.
So
What's up, guys? Welcome, coming in.
And if you once you unplug it, is there the timeline that it would close itself?
Yes. So there is actually a tool. So you can either get the water hose and just let it cool. And it's probably going to take about 15, 20 minutes. But they actually have a magnet where you connect your hose to it. And the magnet gets it's magnetized with the top of the shell. The compressor stays there. Just leave the hose on and it's just going to trickle down. But you're going to take a long time. It's going to take like 15 minutes still. And that switch, it's an automatic switch. It'll just close once it's cooled down. But if you turn it back on again and you didn't fix the leak and it's still under charge, same thing's going to happen. So we're just talking about, Alexis texted me, guys, so don't worry about it, yeah. So we're talking about single phase, permanent split capacitor motors. This is the inside of a compressor. We're going to check it down there. So on a good working compressor, you're going to get this right here, 0.8, 1.2, 2.0. Okay? So resistance. On the back of the compressor, you got 3 pins. Between R to common, the run winding has the least resistance. Your start winding has the middle one. And then when you check run to start, you're adding 1.2 on it. You're adding that, and it should equal 2.0. As you guys do it down there, you guys, it's going to make more sense. But remember, this is a permanent split capacitor motor, okay? So this compressor, it needs a capacitor. So just for now, you guys see that coil here, right? The contactor coil.
Yeah.
So that coil there, imagine there's two of them in there. One is facing like this, kind of vertical, and the other one's at a 90 like this, okay? All right, just like this. This capacitor, remember, current is what makes things happen, right? Current is what makes light bulbs turn, compressors turn on. If the current goes to both the coils at the same time, it's going to get stuck. It won't pump. That compressor will not pump. So how do I get it so that current hits the run winding first and then create a time delay so then it can hit the start winding after, because it's going to go boom, 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 boom. How do I do that? A capacitor. That's the whole job of the capacitor. It creates a little time delay so that the run winding will get hit with current, boom. And as it gets hit, it charges. And then start winding, it discharges on the other side. So current goes boom, run winding, then start. Run, start, run, start. And that's going to make it spin, pump, and work. And I'm going to show you guys down there. If I take out the capacitor out of the circuit, you'll just hear the compressor. That's it. It's just going to hum. So when you have a bad or a weak capacitor, you go to a job and you hear that humming noise.
It's just the fan running.
A lot of the times it's just the condenser fan running.
Fan running,
Yeah. And your compressor will just hum.
yeah.
It'll hum until the temperature, until it gets too hot. Because remember, that run winding is getting all that heat, that current. It's going to just pick up, and the start winding is not getting any love because this is weak. So then it's going to get too hot because current is heat. And then, boom, it's going to open. And then it'll just shut off, at least for a bit. And it does that because now power can go to complete the circuit. So capacitors.
But it won't blow cold air.
It won't blow cold air because compressor is what makes the evaporator to be cold. Yeah, that's what makes the evaporator cold, the compressor. Yeah, good question. So one thing is to make sure all your windings are healthy, right? They should be pretty much the same. If it's like 0.1 away, like let's say this is 0.9 and it doesn't give you 2.1, it gives you 2.0. It's not the end of the world. Now when it's off by a lot and it still turns on, hey, it's turning on. You don't have to replace it. But this is where you want to make sure though, when you go into a job, you want to make sure if it's not hot, okay? It has refrigerant and it's not hot. And you go and check, and this is open line and open line, that's a bad compressor. It's not hot, right? It's got a refrigerant. You check and something happened where it opened like that, you see? Or this opened. You cannot, it's a hermetically sealed compressor. You have to cut it, I don't know, fix it and weld it. It's not worth it. The other thing you want to do, and a lot of people, this is very important, and I was just having a conversation with someone on this, but let me put this back. 1.2, yeah. So you want to make sure this compressor is not grounded. Now, I'll give you the easy way to find out if the compressor is grounded. Super easy, okay? Let's say you go to a job. Mrs. Applebottom calls for cooling, right? Calls for cooling. And then call for cooling, you go outside, and nothing happened. You're like, what happened? Go to the panel, and the breaker tripped. You're like, oh man. If the breaker tripped, that means it pulled a lot of current, more than 40 or 50, whatever it calls for. You're like, okay, something's up. The simple way of finding out, because it could be a condenser fan motor, it could be the compressor. If it's a package unit, it can be it's any motor that pulls a lot of current. What you can do, what I've done, is turn off the breaker, go to the unit, unplug the plug behind the compressor. Just unplug it, okay? Unplug it.
Question before any breaker can be like, for example, my apartment we have the kitchen and the like AC and the same thing. Sometimes I had a back capacitor, and it would take the thing, the kitchen breaker out.
Yeah. So if it's a split system, the condenser, it needs its own dedicated breaker. You will not be sharing it with something else. If it's a furnace up in the attic, it could be sharing it with other outlets in your house. But since we're talking about the high voltage outside, like a 30, 40 amp breaker, something costed to pull a lot of current and it tripped. What you can do though, turn off power, unplug it, and I'll show you guys down there. You unplug it, turn back power on. If it doesn't trip, compressor, okay? You can isolate it. The other way, you need a megger. Unfortunately, this meter here, you cannot check resistance. There's another tool that you can check if it's grounded or not, and I have it down there. I have to show you guys. But coupling compressor doesn't want you using that tool or even that tool that's meant to find ground. They want you to get a megger, and those are expensive. But and there's a little sheet, but basically, you're checking a certain resistance level, and there's a range, and we don't have to get too deep into that. But if you check from run to the metal, right, of the unit or the copper piping, and if it's less than 0.5 millions of ohms, and the megger will tell you that, then it's bad and it confirms it. If it's greater than 0.5, you're okay. But that tool cannot do it. The tool that I have over there can't do it. That's by Subco, like $600-700. But you can go online and find a cheaper one. It just is able to check resistance, but in very high numbers. Detailed, very high numbers, detailed, yeah. But look, if you go to a job, okay, just bear with me right now. If you go to a job, you put it on resistance or continuity. Right, you guys can hear it. If you go to run, and I'll show you guys on there, and you check the copper piping or the unit itself, and you hear beep, it's probably a really bad ground. So you guys have seen compressors, right? The outer shell. Can you do anything with that? Can current make anything work with that outer shell of the compressor? Can you do anything? Does it warp into an animal or make things move? It doesn't, right? That current needs to go to your windings only. But guess what happens when it hits like the metal, the shell of it? You're gonna put too much current. That's why breakers trip. Current's only meant to go to the windings. So make sure it's not open line. Make sure you have it's healthy, and make sure it's not grounded. And we'll talk about it down there once we get to the units. Okay. Any questions with this? Just with this, because I'm going to move on to PSCs now. Same concept, okay? All right, so PSCs, this is the same as this, same concept. It's just that this is a compressor. This is going to be for an indoor motor, okay? So let's go ahead and do neutral, which is my white wire. One, two, three, four. Okay. Boom, boom. All right. All right, and then, okay. All right. We'll talk about this, and then we'll go down to the lab. So this is an indoor motor, okay? So you guys ever have, you guys all have an air conditioning system, and you feel the air coming out of your supply vents? Thanks to this guy right here. This is what helps move air inside your house. Okay? But what are these wires for? Look at all these wires. It's a lot of wires, okay? Just for speeds, correct. But how do you check them? Okay.
Works.
How do you check which one's which? Which one's the fast speed? Which one's the slow speed?
Well, Alexa said the color never changes on these. The black is for fast.
It is.
And then red is for low.
Okay, so you're saying black is fast speed, red is low. But what if you get a universal motor from that comes from another country here, and it has 5 wires? and let's say it's scratched off right here too. How do you confirm with the meter which one's which?
The more resistance you get, the faster it is.
Okay, so the more resistance you get, the faster it is. All right, we're gonna test it. Let's test that, okay? So that's what we get, okay? So look, I'm gonna go ahead and put it on resistance, right? Resistance. So let's check between white, and maybe you can tell me here, Aiden. Between white and black is what?
1.20.
Okay, 1.20. Okay, so I'll put white and black 1.2. 1.2. Okay, let's put all of them. White. All right, so white and black is 1.20. White and blue, what are we getting now?
1.69.
Okay. 1.7. As long as you don't say as long as you don't say 6.7, I'm done. I'm done hearing that. Yeah, I'm so done hearing that. It was just 1.7. Which one did we check? Blue, right?
Yeah.
Blue. To blue. 1.7.
So it's opposite then.
We'll see. We'll see right now. You are, yeah. It is the opposite. So look,
2.6.
2.6. And then white and orange.
2.1.
2.1. Orange. Okay. So the black one is the one with the least resistance, okay? And I don't know, I thought about this illustration this morning, but because the student had a hard time understanding this, but if let's say Aiden, there was a door right here, and you're here, and I'm over here, and I'm adding resistance, and you want to get through, you're probably going to be able to push through. I'm not the strongest guy, but then you get a sumo wrestler from Japan that's 500 pounds, you're going to have there's more resistance. You're probably not going to be able to get through, or you're going to struggle more.
Right.
The key here is, the more resistance, the slower the speed is. Because you have more resistance, current can go, but you won't have too much current. But if you have less resistance, more current can go to that. And more current does more work. And more work, well, the PSC motor with the squirrel cage is going to spin faster. You're going to provide more air. So this part here, black, this is 1.2 between these two. And then it's blue, 1.7. And then 2.1 orange. And then 2.6 red. But it makes sense, right? For me to check from here to here, 1.2. But then for me to go from here to blue, look at, there's more windings to get to blue. This is the way it's wired internally. And so, and have this in mind too. When you guys have a PSC motor, let's say you're only going to use the black one for cooling, and you're not going to use these. Do not wire nut them together. If you wire nut all of them together, the motor's going to go, pfft, that's it, it's gone. Because when this one receives 120, these actually have power, and you can get shocked, they'll hurt you. But it doesn't mean you're not powering these though, it's just the way it's winded, all of them are getting power, but you're powering up that one. Everyone needs a separate wire nut, every single one, okay? Now, same thing too though, right? You also don't want to make sure that it's touching the housing of it. So same thing, you're gonna check with this. You don't really need a measure because the resistance of it's a lot different than the compressor one. But any of these cables to the housing, or you can even check ground, it better be open line. It better be open line, because you only want current going from the power to your windings, and only one winding at a time too, right? We're not gonna be powering two windings at the same time. Motor, it's gone. Only one winding at a time. It's got to be open line. And also too, if you go to a job, So this is simple. If you go to a job and you're checking, it's getting 120, and my capacitor is good too, but it's getting too hot, it's not turning on, it's a bad motor. It's getting power and the capacitor is good.
It's right there.
Also, if you go to a job, you're like, it's not turning, it's not working, turn off power and the shaft. If this is kind of hard to move around,
That's it.
it's bad, it's it. These are easy to replace and easy to diagnose. These are PSC motors, but now for indoor motors, they're using ECM, electrocommutative motors. And those are more expensive, but they're easy to diagnose if it's bad or not, sometimes. But these are like $150 to replace. The ECMs are like $600, $700, $800. It's just so much more money.
You're better off getting a new unit.
Better, yeah. If it's an indoor unit, yeah, it is. It is better. So same thing. Wide to ground. You want open line, okay? Why to ground you want open line? Because this is enough to trip your breaker too. Because can you do anything? Can the metal here do anything with current? Nope. Or just pull more, pff, breaker trips.
There's no load.
There's no load, right? Remember what I said? You got the bloods and the cribs, right? White and black. They cannot touch each other. They must work with the load and they can make things happen. But if they go to each other, that's a dead short. If it rubs off here, it's a short to ground. And those are the two that you want to avoid. So, and one last thing, capacitors. There's no point in doing a class on how to check these because it's only going to take 5 minutes for you guys to understand this, for real. And you got people charging like, I'm not kidding you, it's a $400 or $500 and it's only a $10 part. It's funny because certain companies, I'm not gonna say names because I'm live on YouTube, so I don't want to put anyone on blast right now. Yeah, but there's certain companies, they'll call them like secondary motor starters. Because if you tell the customer, hey, here's the capacitor, it's gonna be $500. And the smart customer is going to be like, what's it called? Capacitor. Okay. $15. Why are you charging me $500? Now, don't get me wrong. Certain contractors do charge $200, $300, $350. You got to pay insurance. You got to pay a bunch of stuff. You know, you got your fee. There's nothing wrong with that. But to charge $500, $600, $700, $800, and I've heard of those stories, that is insane. For this, just for this. But certain companies, they'll call them secondary motor starters. If the customer types that in, they can't find anything. But, you get paid, right? You're not going to be like, oh, just give me $30. No, you got to get paid for it. The customers are not going to be doing this and checking this, and they don't know they have to discharge it, right? You're getting paid for your knowledge and for going to class.
If they want, they can change it themselves.
Exactly.
Which is what I did. I almost died.
You did? How did you almost die?
I forgot to take out the fuse before.
The disconnect?
Yeah.
Oh my gosh.
I'm going off of YouTube video.
Oh my gosh. Yeah. Okay, good. You got to be careful because these right here, even when you turn off power, you got to discharge them. They still have charge. You got to discharge them. And then, look, it's not like it's going to hurt you. But don't be me, right? Don't be like just touching this just because you discharge it. Always be careful. Just be mindful, right, of your surroundings, okay? But like this, it's discharged. But the way these work, super simple. Look, after this, we're going to go down to the lab. But simple, okay? Let's see where I can find space. So right here, I'm going to point. If you look above my my finger, you see the 10 UF plus or minus 6%. Mm-hmm. 10 UF plus or minus 6%. 10 UF plus or minus 6%?
Yeah.
Okay, do you guys see it? 10 UF plus or minus 6%? Yeah? Okay. Look, simple.
Voltage that it gets?
No, it's a different unit or different measurement. So it's simple. So if you want to do it on your phone, it's even easier because you could just type in or put in 10 minus 6%. It gives you the number. But the old way of doing it, you cannot. So what you got to do, you got to multiply 10 with the 6%, right? Plus or minus. But to convert this to a decimal, you got to go back twice, right? So this is the decimal form. So what's 10 times 0.06? I think it's 0.6, right?
0.6.
Okay. 0.6. We just said it's 10 plus or minus 6%. So 10 plus 0.6, 10 minus 0.6. This is 10.6, this is 9.4. My range for this capacitor, if it's healthy, it should fall between 9.4 and 10.6. To check it is MFD, microfarad. Microfarad, okay? Microfarad. Okay, I had it selected. I went to microfarad. Here we go. Let's see what we're getting. Go ahead and check each one, each side. And what are we getting, guys?
8.1.
8.1. Is it good or bad?
It's bad.
It's bad. It's bad. And I actually tried turning on this motor today in the morning, but I started seeing sparks coming from the contactor. So there's definitely stuff going on with this. So I'm gonna just not turn it on right now. I'm gonna get canceled, endangering students. That's it. That's all you're doing. So all these motors, single phase, permanent split capacitor motors, which the type of motor, permanent split capacitor, that's the one you're most commonly gonna be working on. They're gonna need caps. And they need it because run and start winding, the current's gotta hit it, not simultaneously, but with the time delay. Boom, boom. First this one, run winding, then start, then this one, then that one.
Quick question.
And that's what the capacitor does. It creates a time delay.
If it's charged, will it still show 8.1?
Yeah, you just, so if you want to check if you want to check for it, disconnect power, right? Disconnect it. Pull the wires out. Even if you didn't discharge it, though, it'll still be 8.1.
It showed.
Yeah, yeah. But I would have discharged it if you didn't pull wires out, right?
Yeah.
Always be safe. Yeah. So this one here on the start, guess where it goes to my cap. And on my capacitor, this is the symbol it goes to. Herm. Capacitor for this one, it literally says fan. You guys will see down there as we go over it. So fan and Herm.
What does HERM stand for?
Hermetic. Hermetic compressor. And the capacitor for the capacitor for the compressor is going to be a lot higher in microfarads than the fan. The fan needs a little bit. Think about this. Just last thought, and then we'll go down. This is a 10, right? 10 microfarads. The compressors usually take like a 50 or a 60. What's bigger, a park or a stadium? What can hold more people? So just think about that. A park can only hold so many people or less current because it's smaller. A stadium can hold more people, more current. That's why compressors have a higher microfarad, because you need more current going to that start winding to turn it on. Because it's a big component, it just needs more juice. This one, this is a little guy. These are little. You don't need a lot. Very little. So we're gonna go down there, go over the schematics that I have down, and we'll start tracing. We can check the capacitor, we can check the compressor, check the windings of the compressor too, right? We can do all that down there. So, any questions with this? I know you guys. If you guys have any questions, let me know. I know you guys. Alexis told me you guys were gonna be here today, so don't worry about it. But just let me know. If not, let's get a meter and let's head down. And then we'll have to say bye to the
YouTube video.
To the YouTube peeps, yeah. But let's get a meter, guys. Hey guys, gonna head down to the lab now. I'm reading some of the comments. You guys are funny. Oh my gosh. It's funny. I'll have to read. I'll have to read the comments later on. But thank you. I appreciate that, Manny and everyone else. And I just try to keep it simple when it comes to subjects that could be complicated, but you just got to keep it simple. If you teach simple stuff, the students can then learn the more advanced stuff on their own. But you got to build the foundation with the students. So I'm going to start trying to do this every week on different subjects, heat pumps, um, electrical. I had to shoot some content today. So today I'm beat, but I'm glad I was able to do that for you guys. I'm going to try to do this every week. If you guys, I will ask this, if you guys have any suggestions on a good camera, I already have a mic, but a good camera where I can put here, I can walk and we can do a POV with the class. Just I have an email, send me an email or a message here because I've been struggling in finding a good camera. I've been using my phone. So just please, if you can, good camera that gives me a POV. I'm thinking about a GoPro or DJI or DIJ. I think it's called DJI brand or a GoPro. So, and we're located in San Dimas. So I have to head down now with the class, but there is a video that I have on my YouTube that gives you the address. I think it says meet the HVAC Training Academy students, and that one has the address there. But feel free to stop by or show up, or if you want to email me, want to discuss other stuff, let me know. Focus on electrical. I agree. I did videos on. I'm gonna be posting 3 videos this week: voltage, on current, and resistance. So keep an eye on that on YouTube. But I gotta go, guys. I will catch you guys on the next one. All right, take care and be safe out there.